In this last section, I'm going to discuss an alternate way to integrate a function whose relationship between the independent variable or variables and dependent variables we explicitly know. So really this is an alternative to using quadrature or cubature or other techniques that I discussed in the first section. And we're going to be looking at how to do this with Monte Carlo integration method. So first we just want to revisit here something you learned in Calc 1, which was how did we find the average value of a function over an interval. So for this example function here, f of x, to find the average function, we can take the integral of the actual function between a and b, and then the average value is just going to be the integral under that curve divided by its length. So basically what we're doing is we're forming a rectangle from a to b that's going to have the same area as that under the function from a to b. So if we divide out the area under the function by that length, we're going to get what the average value of the function is. And that's a definition from Calc 1. What we can also look at is a way to estimate what that average value of the function is, and we can do that numerically. And this is the part where we're going to be using the Monte Carlo method. So what we do is we take that function, f of x, and we keep trying different values of x in there to see what the value of the function is. And what we do is we take all of those values that we probed, 100, 1,000, a million different values of f of x, and we take their average, just the numeric average of them, and that's our estimate as to what the average value of the function is. Now it's important that when we do this, when we probe this function with different values of x, that we're taking values in the interval, in this case a to b, the continuous interval a to b. That's not always the case if we're trying to take it in a more complicated function that maybe we want a to b and then c to d. But an important feature of this, when we're randomly sampling this function, is we want to use a uniform distribution. We don't want to use a normal distribution or something else like that. So using random values, we can come up with an estimate as the average value. And what we want to get out of this is what is the actual integral under the original function. Again, we might be able to use quadrature. We'll discuss in a little bit why we might not be able to, but we can equate these two values together. So f average on the left in the first equation equal to f average on the left in the second equation. I rearrange it a little bit and I can solve for what is the integral under my original function. So we see what we can do is we can take the average of all of the function calls that we make, and we can multiply it by b minus a, or the length of the function. And that will give us an estimate as to what the area under our original function was. Now here I'm presenting everything as though it's a function of only one variable, in this case x, but this can be extended into functions of 2, 3, or as many variables as we want. In that case, instead of multiplying by the length, like in one variable, for 2 variables we would want to multiply by the area, and 3 variables by the volume, etc. as we go up. Alright, so the better we can have an estimate as to the average value of the function, then we're going to get a better estimate as to what the integral is. So usually we're going to be able to get a better assessment of what the average value of the function is by taking more and more points in that previous step. So in this step here, we're finding f average. The larger big N is, the better that estimate is going to be. And generally, with this Monte Carlo integration, the accuracy of our result is going to scale with the square root of n. So basically, we need to double the number of points we use to get one more decimal of accuracy. We need to double the number of points we use again to get another point of accuracy. So usually it's the case that the more sample points we use to assess the average value of the function, the better, though there is a limit to this, as we'll see once we start to see convergence. Now the quadrature that I talked about, or cubature I talked about in the first section, is sometimes better, or I would say usually better, than Monte Carlo integration for one-dimensional problems for well-behaved, well-defined functions, similar to the ones that we did look at in the first section. It's usually, but not always, quicker to run the quadrature, and the accuracy converges much faster with quadrature than it does with Monte Carlo integration. However, Monte Carlo integration is useful even in one dimension, as we'll see in our examples here, but it's especially good if we have difficult or complicated functions that have discontinuities in them, where quadrature might not behave as well. It's very good for higher dimensional integrals, 2D, finding the volume of something, or things with difficult integration limits it's also useful for. In the example we looked at previously, where we were doing a double integration, we had very well-defined limits between 0 and 5 for x, 0 and 5 for y. But we could have things like a circle or an ellipse that we want to find the volume under, and then it's going to be difficult to use quadrature, and that's where Monte Carlo integration is going to become more useful for us. It's also useful if we do have some sort of function defined by giving it an independent variable and getting out a dependent variable, but we might not explicitly know what that relationship is. So it's a little bit different than when we are in the second section talking about empirical data, where we just are sampling data over time. In this case, we can put some independent variable in and we get some dependent variable out, but we don't necessarily know the relationship between the two. But if we can just get a long list of the independent variables we tried and the dependent variables that came out of it, even though we don't know what the function is, we can see what this relationship is and use Monte Carlo integration in a similar fashion. So again, in summary, I'll just go back here. We are trying to find or estimate the area under our curve in 1, 2, 3, or z dimensions by finding an estimate to the average value of the function on the domain, and then multiplying it by the length, area, volume, however many dimensions of integration we're doing. And we're using random numbers to come up with this estimate as to its average value.